Sometimes when we have two random variables and a third random variable which we can express as a function of the first two, then the joint distribution of the first two random variables can help us get the distribution of the third random variable, which is a function of the first two. So let's let x and y be random variables. And let's let their joint probability distribution function be, let's say, g of xy. Let's define this third random variable, t, to be some function of x and y. Now to find a probability density function for t, we can do the following. A lot like we did for functions of one random variable. First of all, write probability that h of x and y is less than or equal to t. And find a formula for this. Let's say capital F of t as a function of t. So some expression in t. So this might involve evaluating an integral. And second, differentiate with respect to t to get the derivative of this function capital F of t equals the density function little f of t. So for example, let's let x and y have joint probability density function little f of, actually let me call it little g to go along with the example, and to go along with the introduction. Little g of xy equals e to the negative x plus y when x and y are positive and 0 otherwise. It's not hard to check that this is a probability density function. E to the anything is positive, so it's certainly going to be above the xy plane. And if we take the integral as x goes from 0 to infinity of the integral as y goes from 0 to infinity of e to the, we can write this as e to the minus x times e to the minus y. Then we can pull the e to the x out of the inside integral. Then the inside integral is just the density function for a sort of simple exponential probability density function with parameter 1. So that's 1. And we get the density function for another simple exponential random variable with parameter 1. And so that's just 1. Alright, so this is a probability density function. Now let's define t to be x over y. So that's another random variable. So we'll write the probability that x over y is less than or equal to little t. Now x and y are both greater than 0, so this ratio is greater than or equal to 0. So we might as well assume t is greater than 0. So this makes sense for t greater than 0. So this is the probability that x is less than yt. And since we have the density function for x and y, we can evaluate that as an integral. So x is going to go from 0 to yt, and then y is going to go from 0 to infinity, e to the negative x, e to the negative y, and I guess I can put the e to the negative y here because it doesn't have any x's in it, dx dy. So this is the integral as y goes from 0 to infinity. Integral of e to the negative x is negative e to the negative x evaluated from 0 to yt dy. So that's negative e to the negative yt minus negative e to the minus 0. I'll save this part here. So what's this? This is the integral as y goes from 0 to infinity of 1 minus e to the negative yt, and there was an e to the y that mysteriously disappeared. There's an e to the minus y here, e to the minus y here, all of this times e to the minus y dy. So we have e to the minus y minus e to the minus yt minus y. Multiplying exponentials means we add the exponents. Maybe we can factor this exponent to make that integral easier. E to the negative y dy minus the integral as y goes from 0 to infinity, e to the negative y t minus 1. Actually t plus 1. We factor out a negative y here, we've got t plus 1. So this is just 1, that's the exponential density function, minus, well, this is almost exponential. If we write t plus 1 e to the minus y t plus 1 dy, this would have area 1. So I multiplied by t plus 1 on the inside, I'll divide by t plus 1 on the outside. And we get 1 minus 1 over t plus 1, and this is just 1. So this is our cumulative distribution function for t. Now the density function, little f of t, is just the derivative of capital F of t. Derivative of 1 is 0. Derivative of t plus 1 to the negative 1 is t plus 1 to the negative 2 multiplied by negative 1. Actually, we've got a minus here. So we bring down the minus 1 that makes it a plus. So we have 1 over t plus 1 squared as the density function. Now if we wanted to find the probability that t is less than 4, for example, we could integrate this from 0 to 4. Or since we already have the cumulative distribution function, we could just plug in 4 into that. So 1 minus 1 over 5, so 4/5. All right, let's do another example. Let's choose a point at random inside the circle x squared plus y squared equals c squared. So it's a circle of radius c centered at the origin. And let's let r be the random variable. So let's say this point at random is capital X, capital Y. And let's let r be the distance from that point to the origin. Let's find the expected value of r. So to do this, we'll find the cumulative distribution function for r. And then the probability density function for r. And then we can use that, multiply it by r, and integrate to get the expected value. So the cumulative distribution function is the probability that this random variable r is less than some value little r. We don't need any integrals to do this because we can just draw a picture. So we have this circle of radius c centered at the origin. And then we're closer than little r to the origin if we're inside a smaller circle of radius, little r. So the probability that we're in this little circle, given that we chose a point in the bigger circle, is area of the little circle, pi little r squared over area of the big circle, pi c squared. So r squared over c squared. So little f of r is the derivative of big F of r, which is 2r over c squared. So that means we can find the expected value of r by taking the integral as r goes from 0 to c of r times 2r over c squared dr. So let's see, 2 over c squared is just a constant. We can put that on the outside of the integral. And so we're really just integrating r squared dr. So we've got 2 over c squared. The integral as r goes from 0 to c of r squared this is C, and that is R cubed over 3 evaluated from 0 to C. So we've got 2 over C squared, C cubed over 3 minus 0 over 3. So just C cubed over 3. Canceling C squared from the numerator and denominator, that leaves us with 2C over 3. So I guess we expect the randomly chosen point to be 2/3 of the distance from the origin to the bigger circle. The end.